Welcome to The Explainer. Today, we're going way beyond just crunching numbers. We're going to learn how to write a program that isn't just code. It's more like a cosmic symphony, composed in the language of the universe itself. I mean, really think about that for a second. Forget the usual rigid ones and zeros that we're all used to with classical computers. Just imagine, what if, at their very core, computers could move with this kind of fluid grace, this boundless possibility, just like a dancer. And that's really the heart of quantum computing. It's a machine that doesn't just spit out one single answer. No, it explores a whole landscape of potential answers, all at the same time. It kind of operates in this shimmering state of what could be. It really does sing. Okay, so how do we get to be the choreographer for this incredible dance? Well, we start by learning the fundamental moves. And in the quantum world, these moves are called quantum gates. They're our key to conducting this whole cosmic orchestra. It's really important not to think of these gates as just, boring technical commands. Each one is a fundamental, elegant move, and when we start combining them, that's when we create the full performance. All right, let's start with the basics, right? The solo performers. We're going to look at gates that work on just one single qubit at a time. Each one has its own distinct, fundamental role to play before we start creating any duets or, bigger ensembles. First up, we've got the X gate, or as you might know it, the quantum not gate. The best way to think about it is like a perfect pirouette. It takes a qubit and just spins it 180 degrees, flipping it from a state of 0 to 1, or from 1 right back to 0. It's the most basic flip in our entire choreography. It's a totally foundational move, really the basis for our whole quantum choreography. Okay, now for something a little more subtle, the Z gate. This one's kind of like a mood swing. The qubit state, you could call it its face. It doesn't change. It doesn't go from 0 to 1. It stays right where it is. But its internal property, its mood, or its phase, gets a little twist. It's a very quiet move, but it's absolutely crucial, especially when qubits start interacting with each other. And next up, we have the Hadard gate, or H gate. Now, folks, this is our wild card. This is where the real quantum magic starts to happen. The H gate takes a definite state, like 0, and puts it into a perfect superposition, a state of being both 0 and 1 at the very same time. Just imagine a spinning coin caught perfectly on its edge, being both heads and tails at once. That's what we're talking about. So we've seen what the soloists can do, but what happens when they perform together? Well, the most profound, mind-bending effects in quantum computing happen in the duet, where a very special gate can link two qubits together in that mysterious, powerful state we call entanglement. And that's pretty much the essence of the C-NOT, or controlled NOT gate. It's a conditional instruction. It connects two qubits, a control qubit and a target qubit. The logic is so simple but so powerful. The control qubit looks at its own state, and if it's in the on or 1 state, it tells the target qubit to do that X-gate pirouette we just learned. But if the control is 0, the target does absolutely nothing. So this is how you combine the moves to create something with real quantum power. The recipe for entanglement is actually this beautiful 2-step dance. First, you use a Hadamard gate on 1 qubit, which puts it into superposition. Then, you use that qubit as the control in a C-NOT gate to influence a second qubit. And the result, well, it's profound. Their fates are now intertwined. They echo each other no matter how far apart they are. Okay, so we've got our dancers and we know their moves. But how do we write it all down? How do we organize all these gates into a complete program? Well, that's where quantum circuits come in. You can think of them as the sheet music for our quantum symphony. And the good news is, reading this sheet music is actually pretty intuitive. Each horizontal line, or wire, represents the timeline for one single qubit, and it flows from left to right. The symbols that we place on those wires, those are the gates, the specific actions or dance moves that we apply at very precise moments in time. So let's take a look at our entanglement recipe, but this time written out as a circuit. Here, Q0 and Q1 are our 2 qubits. First, on that top wire, you see the H in the brackets. That's the Hadamard gate being applied to Q0. Then, see that vertical line connecting the two? That's our C-NOT gate. The little dot on Q0 marks it as the control qubit, and the plus symbol in the circle on Q1 marks it as the target. This simple little sequence, this is the language of our cosmic symphony.
All right, so after all the spinning and twisting and entangling, how does the performance end? It ends with measurement. This is the finale. It's like a big percussive final note that collapses all that shimmering possibility of superposition down into one single concrete outcome. We finally look at the qubit and it's forced to choose. It becomes a definite 0 or a definite 1.
So there you have it. You have the tools now, you understand the soloists, the duets, and you know how to read the sheet music. It's your turn. It's time to be the composer. Think of this as your new creative toolkit. You have gates to flip states, to twist their phase, to create the incredible magic of superposition, and to entangle qubits together. With just these 4 moves, you've got the fundamental building blocks to start composing. And what's really fascinating is that this language, this music, it's universal. The circuits that we design can be played on all different kinds of quantum computers. Some use delicate microwave pulses on superconducting loops. Others use incredibly precise lasers to manipulate trapped ions. The instruments are different, but the melody, the actual logic of the circuit, it stays the same. So I want you to remember this. When you arrange these gates on their wires, you're doing something, well, it's profound. You're not just programming a machine. You are literally sculpting probability itself. You're designing a delicate dance to guide the universe toward an answer. You now have the first few words of a language that, honestly, until very recently, only the universe knew how to speak. The power to search, to discover, to create, it's all rooted in these simple moves. So the question isn't really what a quantum computer can do anymore. The question is, with these tools now in your hands, what will you create?